All right. Hey, everyone. I'm Ina, and the fourth hands-on session is going to be on velocity field curves in gallium arsenide. So I believe Ivan talked about this yesterday. And so, and he recently published this paper where he was showing that you can calculate the velocity or the drift velocity for very high electric fields, basically. So this is a plot from his paper. And this is specifically to gallium arsenide. And he was able to show that he can simulate the linear increase in drift velocity as at low electric fields, and then the peak and then decrease in drift velocity at high electric fields, which is something called the gun effect, which happens in gallium arsenide because of its band structure. And so basically, I'm going to show you a very, very simplified version of this calculation because the actual calculation would take way too long. But yeah, so we're basically going to try and calculate the drift velocity in gallium arsenide. So the drift velocity is given by this equation right here. And specifically what we need to calculate is the carrier occupation. So this F subscript nk at times going to infinity, because we got the steady state drift velocity. So in reality, we're just going to kind of let time progress to like a reasonably long time where we feel like our occupation has converged, like it's not changing along with time. And then Perturbo will actually calculate the drift velocity and output this in the YAML file directly. But basically what we need to run is the dynamics run and the dynamics post-processing calculation modes. So that's what I've been showing you in this hands-on session. So first, there's some setup steps. You've probably done a fair few of these already today. But basically, if you haven't already today, please do a git pull in the Perturbo Workshop GitHub repo. And then I presume you've all installed Perturbo-Pi at this point. So we've got that. And then I hope you've all downloaded this gallium arsenide EPR file. The link is right here if you haven't, but it is a 1.7 gigabyte file, so it would take a while to download. And then, yes, we need the Docker, basically. So if you're all ready, just start off your Docker, basically, in this, the i4 version or the GCC version, depending on which one you use. I believe I've already actually started up Docker, as I see in my terminal right now. And just a heads up, if you do just decide to copy paste this link, this command, then please change out the location of this GitHub repo on your local computer. Otherwise, it's not going to run. So is everyone ready with the Docker and everything? Okay. Right, so what we're going to do first is that we're going to just move into the hands-on 4 folder. And if you do an ls, there's a QE to Pert folder there. So please copy paste or link the gallium arsenide EPR file into that folder, because that's what everything's going to be linking from. Why do you have to test? That was for my own testing purposes. That's not in the GitHub repo. So yeah, let me know when you're all ready with the gallium arsenide EPR file in the QE to Pert folder.
A quick question about the GitHub tutorial has some demo EPR file. Why is it like different from this?
So this one's bigger. This one's one
What
point.
was set up actually?
So this is actually just straight out of our tutorial on the website, basically. And I believe in the setup, it's just a larger K grid or Q grid when you run it in Quantum Espresso, basically. And then when you also created the QE2 pet, there's just going to be higher samplings, basically. Whereas I believe the one Yao did was probably a lot lower sampling, so that you could actually run it in real time. But yeah. So is everyone ready-ish? Okay, so when you're ready, we're going to move into the Perturbo directory and then into the band directory. And we're just going to plot the bands, basically. And so, as you probably have been explained today, there's two input files for the bands calculation. There's the pert.in. You can open this in your terminal if you like, but it's right here. So there's the prefix gallium arsenide, calc mode bands, and then the FK list, which is this other input file, which just lists the high symmetry points that you're going to plot your bands against. And so we can now just go ahead and link the EPR file from the QE2pert folder. So that's in our bands directory. And then we can go ahead and run Perturbo. And so you're going to again specify the number of OMP threads, which on my computer is 4, but set it to whatever writes on your computer, and then run Perturbo. And that should be relatively quick. And give us an output file. So just as a quick check, we can check that it did actually run as it should have. It did. And then we now have both the YAML file and this gallium arsenide.bands files. And then we have this little Python script that we can now run to just plot the bands. So you can just run that with Python 3. And that should create 2 image files. So this gallium arsenide underscore band and gallium arsenide underscore band soon. So the reason I've done that is the first one is just the gallium arsenide band structure, all the bands we're calculating. And then I've just done a zoomed in version of it, basically. So this is something Perturbo lets you do. You can just specify kind of the range of energies. And this will be useful just because we're going to, again, set an energy window for our calculation. So I've just zoomed in on kind of, we're going to be calculating for the first conduction band, basically, the lowest conduction band, which is this one, or this one here. And so I've just zoomed in so you can kind of see where the energy window is going to be set, basically. All right, so now we need to do the setup calculation before we can do the dynamics calculation. So that's in order to calculate kind of our K-space sampling to reduce the numbers so that we can use all the fancy summation integration things over K-space that the Perturbo already has integrated in it. So go ahead and move out of the bands directory and into the setup. And in here, you will find a pert.in and gallium arsenide.temper. And then this pert underscore accurate, which I will come back to later. But yeah, if you go ahead and look at the pert.in, we have the calc mode is now set up. We have K dimensions 60 cubed. And then we have set the energy window to be this, which will effectively kind of put you somewhere like here, I guess. And then we're only going to calculate for the lowest conduction band, which is the 5th number. And then we have the temper file, and then we set hold to false because we're calculating for the electrons. And then we also have the temper file, which looks like this. And in this case, the only thing we really care about is this temperature, because we're actually calculating for the occupation. So we're going to set, basically in the dynamics calculation, we're going to set what distribution we start out with. So we're going to set both the temperature and the chemical potential for the electrons in the dynamics run file, input file, and not here. So the only thing that kind of comes out from here is the temperature that's going to be used for the phonon distribution. Not used in this case. So they're just set to some random number, and they're not going to be used.
How do you, like, what is the code doing right now if you do not need these two?
So in this case, in the setup part, it's only going to be calculating kind of your K-space sampling. And so basically what it's doing is using this energy window. So it's using the K dimensions to kind of sample your K-space. And then it's using the energy window to cut off like any K values that's going to give you an energy much larger than or lower than your window. And so it's going to say, okay, we don't care about those K points basically. So it's then going to basically just create K points that you're going to be calculating over later.
Okay, so this will be saved for later.
Yeah. So this is what's going to give you the TET output file, which is going to be used later, basically. All right, so with those two input files, we can now go ahead and run the calculations. So first we need to again link the EPR file. All right, and then we can go ahead and run Perturbo. And this should again be reasonably quick. And so I was kind of saying the main output from the setup calculation that we care about is this. Sorry, not this one, this one. This gallium arsenide underscore tap.h5. Because that's giving you the K points basically that you're going to be needing to kind of sum over K space later. But it's reducing them so that you're not calculating for all possible ones, basically. It's reducing them based on energies and symmetries and various other things. And so I think if you actually open this gallium arsenide.
Do you have the option of running sampling in this case, or if you cannot use one?
No.
Why?
Kelly.
You have to have momentum conservation. Okay. And for the intermediary argument, we are using exact conservation to align all the exactly listening. So this here is the moment. And when you put values in your own insurance conservation, but not. That's why a super dense rated method. Yeah.
So this, I just opened this gallium arsenide underscore tet.kpt file, so not the H5 file. And you can kind of see here that basically it's able to reduce the number of K points to 154. Whereas normally if you didn't have this like energy window and stuff, like you'd be looking at 60 cubed K points. And also it's also using symmetries to reduce those points, basically. But that gives you kind of an idea of why we do this stuff. All right, so I mentioned that I also have this underscore, so the per underscore accurate.in file in here. And the idea there is because, as you will see later, this is a very, very simplified calculation. I've got a very small, in this respect at least, small energy window, and also just small K sampling, just so you can actually run this in real time. But if you want a more realistic, sorry?
Question.
Yep.
in perf.in, the max is smaller than mean energy.
It shouldn't be. I think you might miss the 5 in front.
Oh, sorry.
No worries. Yeah, otherwise that wouldn't work.
Okay.
So that's fair. All right, so yeah, but it is a pretty small energy window, especially once we actually start adding in the high electric fields. And so you will see by the end of this that our calculation isn't particularly accurate. And so I've kind of added this per_accurate.in file, so that if you wanted to, you could run a much more accurate calculation, but you can't really do that in real time. And I think when I tried it on my Docker, it crashed. So you would most likely need access to a cluster, but the file is there if you want to like do it later in your own time. But mainly the key point is that I've increased the energy window so that you can see the full field basically. And then I think in the paper, I even used like 160 cubed K points. So yeah. All right, so we've now run the setup calculation. So now we're finally ready to do the dynamics run calculation, which is actually going to be calculating the occupations for us with respect to time. So this is F subscript and K of T. So just go ahead and go out of the setup directory and into the dynamics run folder. Everyone with me so far? Any more questions? All right. So the key point now is that we actually want to calculate for different electric fields. And so what we'll have to do is basically do one calculation for each electric field strength. And then for each electric field strength, we want to run it to a time where the occupation kind of converges, which is what we kind of classify as like steady state. And so this diagram here kind of shows what we're going to be doing. So we're going to start off with the 0 electric field, and we're going to run that till we get converged occupation. And even though technically, from a physical perspective, you should be getting 0 drift velocity, we have to do this because numeric issues means the occupations might be a bit iffy to start off with, so we just need to converge that too. And then we go ahead and increase the electric field, and then we run that to convergence, and then we restart it from that occupation when we then increase the electric field further. And the reason we do that is because that way there's smaller jumps and it takes less time to converge for each electric field, basically, even though you could restart it every time from the 0 electric field, but that way you would have to run it much longer until you get the convergence for each kind of increase in electric field. So that's why you kind of do this like step process. And so to kind of do this all in one go, I've created this shell script that's the run.sh, which lets you kind of run it for all the electric fields without you having to restart it each time. So because this calculation is pretty time consuming, we're gonna go ahead and just start running it, and then I'll explain the input files as that runs. So just go ahead and make that executable by running this command. And then you should be able to run it. Whoops. And then that will sit there and do its thing. All right, so the input files. Is everyone good? Did everyone get that one to run? Okay, cool. So the main input file is the per-ref.in. So this is just the general input file for a dynamics run calculations. You can see the calc mode is now dynamics run. And then again, we have the K dimensions to be 60 cubed. But in this case, I've specified the dimensions of the phonon grid to be 10 cubed. And again, this is to try and reduce the calculation time. Again, if you wanted more realism, you might want to increase that. Like Prue said, it needs to be commensurate with your K dimensions. And then we have this new parameter now called volts underscore E field, which is specifying your electric field strength in each of the dimensions. And so initially this is just set at 0, but this is one of the parameters we're going to be changing in the shell script to the different field strength we're going to be plotting for. And then we again have the energy window and specifying the band. We have poles set to false and the temper file as before. And then here are the more specific parameters relating to the dynamics run calculation. So in this case, because we're iterating the Boltzmann transport equation, we need to set a time step, which I have here set to 20 femtoseconds, which is very large, again, for time constraints reasons. As you will see in the accurate one, it's set to 2 femtoseconds, just to kind of give you a comparison. And then the bolts underscore n step gives you the number of steps we're going to run it for, so the number of time steps. And then output n step gives you the number of, well, after so and so many number of steps, it's going to output to your H5 file, the C dyna file that will be written from this calculation. And then we have these init parameters. And so this is where we're specifying the temperature and, so this is how we specify the occupation of the electrons, the initial occupation, basically. And so we set it to be the Fermi distribution. And then the init smear is going to give you the temperature in your Fermi direct distribution.
This is parameter, which corresponds to the temperature, which is T.
Yeah.
Okay. So you have to manually set it and calculate. This is 300K, right?
Yes.
Okay, so this is MEV.
Yeah. So I guess technically you could set the temperature in the temper file to be different from like the smear here, and you would have a different temperature for the phonons and the electrons, but I don't know exactly why you would want to do that. Do you know, Callie, if you could do that? Yeah. So, and then you have the init underscore E0, and that gives you the chemical potential. And then there's this load scatter EPH. So that's what Drew was mentioning. Initially, we set this to false because for your first calculation, you do need to calculate the scattering matrix elements. But as you will see once, and this is why this is taking so horrifically long, is because in fact it is calculating the electron phonon scattering matrix elements. And what's going to be key when we try and do when we then going to calculate the other electric field strengths, we're going to set this parameter to true, and we're just going to load those, and those steps will be much quicker, basically. And again, you have to then specify the temp directory so that it knows where to load those elements from. And then
question, here you set pole to false, and there is a corresponding electron path. Right? If you want to calculate for pole,
so if you wanted to calculate for holes, you'd set it to true.
But
and then you'd have to set the band accordingly.
Oh, the band should also be.
You would then
4.
have to specify, yeah, 4. Yeah, exactly.
So this package just adding a minus sign. Then how can you handle it if for matter there, like the second matter there is both electrons and holes?
Kelly?
So you can model the dynamics differently. Better, I think you do one because there so there's the need of polarity and on the back. So this one is the machine. So you can quickly do the whole is true and the spin with your whole, and then you can really have your second. So it's really a 2 step.
Yeah.
Yeah. Is it additive? Is it really additive to the results? Yeah, because okay, let's see.
And then,
how do you get the chemical potential? This is not. Where is it?
oh, you set that. That's basically, you set it here. So you just choose where you want it.
Yeah. So in the setup folder, I don't get this.
Yeah, you don't set this. So that's normally you would set that in the tempo file in the setup. But then because the only thing we care about from the setup calculation is just kind of how we sample the case space. So you don't have to set it until here in the case of the dynamics calculations, basically.
Then how do I know what concentration it is? What kind of concentration?
So in that case, you might have to go back and calculate the RTA, basically, to calculate the concentration. Yeah.
Does it still apply, like in RTA? You're in high field in this case. Are you sure the same result maintains?
I mean, the concentration should be the same, yes.
Okay.
Because otherwise you'd be adding electrons from somewhere.
And another problem I run into is I cannot open temporary file. Permission denied. I'm not sure if anyone has this problem.
Oh, interesting.
So by running this right after the
so let me see. Can you check the pep.ref? Oh, sorry, pep-ref file.
This is
So for everyone else, the last few parameters is the Bolt's norm distribution. That's just making sure that you normalize your distribution so that, again, the concentration actually does stay constant. And then the solver is set to Euler. So for the paper that I referenced, I even actually implemented new solvers, but I'm not sure if they're available in the public version yet. So for right now, we have the simple Euler kind of solver to get the time steps, basically. And then this last parameter is also very useful. I haven't been able to show this here because of time constraints, but basically what this parameter lets you do is that it lets you tell the program that it's going to self-check when convergence happens. So basically, if this is turned on, then you can say, okay, once it's like changing by this much, then we say it's converged, then you just drop out. So then basically you could set this like number of steps parameter to be like several thousands, and then the calculation will just drop out as soon as it's decided that it's converged, basically. And so you wouldn't have to guess how many steps you have to keep running for. But again, because to actually converge this, you might have to run for a large number of steps, which I don't have time to show. So we're just going to ignore that parameter today. But again, feel free to test that at another time. And then comparatively, like I said, for the accurate file, the main two things that are changed is the energy maximum and the time step and the number of steps to get it to give you a much more accurate result, basically. But again, as you can imagine, this would increase the number of K points, and we're having to do many, many more steps. So it's a much lower calculation. So
I recall the tutorials that so far we have multiple choices.
yes, exactly.
This one is faster.
Yeah, so the Euler is like the simplest one. But yes, I think
does it compromise the accuracy?
Possibly, yes. I think Ivan again in his paper used an RK4 solver for some of the steps. He kind of used a smarter solver for the first few steps and then kind of went back to the Euler when it was like getting close to convergence. So yes, that is again something you can test to see if your results improve or not. But yeah, the Euler is the simplest one. And I'm not entirely sure, Kelly, do you know if Ivan's released the new solvers?
Yeah, the solvers that we talk about in paper, they're not released, and they might be released in future releases, similarly to the solvers Kelly was talking about from the Sandals library. So currently we provide the Euler and Runge-Kutta. But talking about the solvers, we can say that as soon as we decrease the time step, we make it smaller, the solution become more accurate. So any solver in the limit of delta t goes to 0 will give you the same result. So if some kind of sophisticated solver does well at 50 femtosecond, well, Euler might do maybe the same job at 1 femtosecond, but still you can arrive at the same result ultimately.
Right, so my calculation actually finished before I got to the script, but this is basically the script that we've been running. So this is the run.sh file, which is just a bash script. So the prefix, we set it to gallium arsenide, and then we set the number of electric field strength. So what you've been running it for is the 0 field. But then what we're going to be doing next is we're going to uncomment this sequence going from 200 to 1600 in steps of 200. But you could also, if you wanted to do this another time, you could basically just uncomment this, which lets it run from 0 to 1600 in one go. I just did it this way so I could explain the script whilst it runs. And then it also specifies the OpenMP threads, which again, this one is something you might want to change if your computer has a different number of cores. And then it does a for loop over the E field strengths. And for each of them, it creates a directory called E field dash like the strength of the field. So basically, once your calculation is finished, you should be able to see this E field dash 0 folder. And then once it's created that folder, it moves into the folder, and then it copies this pert-reference.in file into the folder and calls it just pert.in. So if you do an ls, you see this pert.in file basically. And then it goes ahead and makes some changes in the input file. So first of all, it changes the electric field strength. So it looks for this parameter, and then it changes it to the electric field that we're currently running, like looping over. And then in the case that you're not running for the E equals 0, it will change both the volts init distribution and the load scatter EPH. Basically, the volts init distribution, it will now set to restart, so that you're basically restarting from the last occupation you had when you ran it for the previous field, basically. And then the load scatter EPH is set to true so that it loads the electron phonon scattering matrix elements that you've already calculated. So this way we can basically skip that whole calculation and it will massively speed it up. And then it links both the EPR file and the TEP file, and it copies over the tempo file. And then again, if your electric field is not 0, and we are in fact restarting and also using this tempo file, or tempo folder rather, sorry, not tempo, temporary folder, then it will also go ahead and link those. So it's going to link the cDyna file, which is the output for the dynamics run calculation, and it's also going to link the TMP folder. And then the idea with that is that then for each of the subsequent runs, they're just going to print to the same cDyna file. And I will show you what that looks like afterwards. But yeah, and then it just kind of loops over each of the field strengths. So what we can now do is we can just open this run.sh script, and we can in fact comment out, whoops. the E field equals 0 and uncomment this range. And then we just close it. And then we can go ahead and run it again. And you should be seeing it's now going much faster. Were you able to get it to work? No. Mm. There's some permission issue basically?
It's sort of permission, but it seems like like that's files.
Oh, that's weird.
We said if it's serial, it will reduce the previous result. But if it's MPI, it will restart from scratch at the time.
No, so it doesn't have to do with whether it's like serial or MPI. It's only what I've set it to do in the script, basically. So it's basically an input parameter. So the bolts init distribution tells it whether you can set this to restart, and that tells it to basically use the occupation that it had in the previous run, basically. And then just start with that occupation and run with that, basically. So that's kind of going back to what this diagram shows, that you run, so let's say we're here, basically, we're going to start with the family distribution, and then we set the electric field to 200, and then we let it run over some time. And then once we then increase the electric field to 400, we've set it to do bolts init equals restart, which means it's basically just going to pick this last occupation that it had in its previous run, and then just set that as the initial occupation, and then it kind of just runs from there. And iterates from there, basically.
But currently it's still Fermi.
It starts off with Fermi.
Starts with Fermi. I mean, for the higher temperatures, it's still Fermi. It's not start from the 100.
So we're not changing temperature. Temperature's the same. We're changing electric field.
Sorry. It starts
From the electric field, no, you're not starting from the Fermi distribution. You're only starting from the Fermi distribution for the 0 electric field. And then for all subsequent electric fields, you're starting from the last distribution for the previous electric field.
And it's done by restart.
But that's done by restart.
Okay, so it's
So you can kind of see this from the cDyna file. So I've got this it's like HDFU program that you can download that lets you view these H5 files, sorry. And so you can see this final cDyna file here. So when you run all the calculations, and it's run for 0 to 1600, which is basically 9 steps. And so for each step, the cDyna file will have this dynamics run folder, and then it will have the time steps that it outputs for that specific run. So each run is equivalent to an electric field string, and then each time step is just the output at that time step, basically. So if you then went ahead and double click this, it's just going to be slow, but yeah, you will then actually get the occupation at a specific band and K point is what this shows you, basically. And so what this means is that at this snap T0, it is the Fermi distribution, but then you iterate the Boltzmann transport equation so that by the time you hit the 20th step, you have a different distribution. And then the idea is for the second run, because it's now set to restart, it's basically just going to pick whatever the occupations were here in the 20th step and use that as the start, and then and then iterate that basically. So that's what it's doing. So has everyone been able to run that and it's run to completion? You've got all the e-fields. So you should be ending up with something that looks like this, with a folder for each of the field strengths. And inside each of them, in the case of like the non-zero field strength, you should see that it's actually linking the cDyna file and also the temporary folder.
Excuse me, if I understood correctly, was there a problem with the SED on one of the participants' computer? The permission problem?
Yes, I think so. Right.
Okay, so I don't know if you managed to find a solution. So I think that one was related to some strange permissions on a given machine, and with the fact that SED was doing -I, so in her script was doing this in place replacement, right?
Mm-hmm.
So if you avoid that and just do SED and then output this SED to another file and then move this file to Pert, which is longer, but then I think it could work. So I can write this solution on chat. So these lines can be just replaced. So instead of doing SED -I, you could do these lines with a SED, and that should work.
So if you go into the chat, oh, you're not on Zoom. Okay.
Yeah, so that's a question then how we would share these lines with the participants, maybe.
Yeah, could you help with this, Kelly? Perfect. Yeah, he's talking about these lines basically.
Yeah, how should I change this one?
Thanks, Ivan.
Sure.
All right, so for everyone else, have you managed to get the various folders and run the script and everything? All right, so then we can move into the post-processing step. So just move into that folder. So that's the dynamics.pp, sorry, -pp. And in this case, we have a pert.in file again, which is basically the same as the pert.in for the dynamics run, but now you don't have all of these like time stepping parameters. So we're now just back to like the K dimensions, the electric field, the E min and max, the band min and max, hole, and F tempo. And what's specific here is that you do in fact need to actually specify a non-zero value for the E field. So this post-processing step will still use the actual E field that you used in your calculation. It won't just use 200 for every single one of them. But it needs to be set to not a zero value, because otherwise it won't output the drift velocities to your YAML file. So it's kind of like a bit of a weird turning on and off whether it should output drift velocities. So that's why this is just set to 200. All right, so now to run this, we can go ahead and link the EPR file, the TEP file, and the cDyna file. And so in this case, you will want to link the cDyna file from within the efield-0 folder. So you can just copy paste this if you like. And then we're going to copy across the temper file. And then we're going to go ahead and run Perturbo. Whoops. And that should be reasonably quick. And then the key outputs here is the YAML file that contains the velocities. And then this POPU or population file. And that contains the occupations, or the average occupations at each energy, basically. And so what we actually want is, in order to plot the velocities, is this YAML file. So if you just go ahead and open that, we can do a search file. And here are the drift velocities, basically, for each time step. And then we can go ahead and use this Python script that I did not update on the GitHub, but it is in here. So basically just go ahead and run this plot vel field curve. And what this does is that it creates this velocity field curve.png. And if I actually open that one, you will see that it uses Perturbo-code to extract the drift velocities from our YAML file. And this is very useful because the YAML file has the drift velocity for every single time step. So basically for all of the runs kind of concatenated together. And we only want the last one at each of the runs. So Perturbo-code just goes ahead and extracts those for you by using this extract steady drift law. And then just plots them basically. And so if you go ahead and open that PNG, this is what you'll see. And so it's kind of what we wanted. It's not particularly linear right here. It does have a peak and then it does dip, which, you know, we would maybe think was the gun effect, but however, it does dip down to like a minus value. So if one of the ways we can kind of inspect like what's happening here is that we can plot the occupations. So that's this plot right here, and you can plot that yourself if you want by running Python 3 on this plot occupations script, and it should give you this image right here. And so these are the different occupations for the different fields. And so I haven't actually labeled what the colors, like what field that signifies, but you can kind of sort of guess just from looking at it that this first part here is the 0 and kind of small fields, and then as we move up to higher energies is the higher electric fields basically. And the key part that you want to take, like that we can see from this, is that we actually get like our energy window isn't large enough to get the whole occupations once we're at higher electric fields basically. So you can see here that clearly some occupations that are getting excluded. And so this kind of explains why we have this insane dip at higher electric fields, because they're in fact not even included in the calculation. And so on our cluster, I went ahead and did the more accurate file. So if you were to actually run the per_accurate.in files, you should be getting this sort of occupations. And so, as I said, the key changes that I made was I increased the energy window. And so in that case, you can now see that I increased it to like almost 6.9 electron volts. And in that case, the whole occupation is actually within my energy window. So I'm not cutting off anything anymore. And then if you were to do that with the same time step, with the 20 femtoseconds time step, what I found was that I got this weird behavior around this energy. And so that's just a matter of you just having way too large of a time step. And so that's why it's set down to 2 in those more accurate versions. And if you were to run those and plot the drift velocities, then you should be getting this sort of curve. And so in this case, because we now don't have any cutoff of the occupations, we can see that this dip is actually more physical and probably actually indicating the gun effect like we wanted. But yeah, if you wanted an actual properly accurate, you would also have to increase the K and Q dimensions, amongst other things. So yeah. But, all right. Any questions?